for lesson 4, which is covering the central limit theorem. This is a theorem in statistics that allows us to take our normal distribution methods and allow us to use them on problems that might not necessarily be normally distributed. So these problems are going to revolve around a random variable x that may or may not be normal. We do know its mean is mu and its standard deviation is sigma. The idea of the central limit theorem is founded on this idea of taking simple random samples, all of the same size, from a given population. This results in something called a sampling distribution. Here's a picture that might help you understand a sampling distribution. This takes a greater population and finds smaller sample means. All of these sample means are going to come from the same size sample. So maybe they're all from a sample size of 3 or 5 or 20 or 100. And what we do is we take each of these sample means that were found from taking subsets of this population, and we use them to form a brand new distribution. What's really interesting about the central limit theorem is if n is large enough when you take all these sample means and create a new distribution, it starts to form a normal distribution no matter what the distribution started as. Obviously, if the distribution started normal, it'll stay normal, and as n gets larger, so n is 2, n is 5, n is 30, you see that this distribution just gets narrower and narrower on the way down. The middle of the distribution stays in the same place. That means the mean is staying consistent, but the standard deviation, the width, is getting narrower and narrower as you go. You'll see the same thing with another distribution, the uniform distribution. As you raise the n to size 2, you start to get this little triangle shape. As n goes up to 5, we see we're getting pretty close to normal, and by the time we're at n equals 30, we have very much a normal distribution. This happens with the exponential, this happens with the parabolic, it happens with any distribution. As n approaches 30, the shape of the distribution formed by finding a bunch of little sample means becomes normal. Now that information might not sound that important, but it's going to open up a lot of doors for us in terms of what tools we can use to solve problems. Based on the pictures we were just looking at, if n is greater than 30, we know the sampling distribution is going to be normal. In all cases when n was 30, we saw a normal distribution at the end. If n is less than 30, but the original started off normal, we see that anything that started normal stayed normal, so it can still be treated as a normal distribution. If n's less than 30 and it was not normal, then the methods of this lesson don't apply. Some important conclusions before we move forward. The mean of the original population will match the mean of the sampling distribution. That was really easy to see with normal in that the middle stayed the same throughout all 4 of the curves. But it's also true for any other distribution. It sounds crazy to say, but the mean of the means is always equal to the mean of the population. That's not true for standard deviation. The standard deviation, as we saw, it changed. These graphs got narrower and narrower as you worked your way down. That means the standard deviation was getting smaller and smaller. Well, there's actually a formula to determine the standard deviation based on the size of n, and that's sigma over root n. As n gets larger, you're dividing by something that's bigger, and that makes the result smaller. So that's some complicated information. So why do we care? Well, as you'll see when we start to do problems, this idea that a sampling distribution becomes normal will allow us to use our normal methods to solve problems. And since all distributions will become normal if n's large enough, it means if n's large enough, we can use our normal methods to solve any problem. That means our calculation power becomes endless. So let's start getting into some actual examples. This first problem gives us some information about the population of weights for men, and then asks us to solve a problem finding the probability that a man weighs greater than 175. This is actually a problem from lesson 2. In that lesson, we drew a picture showing weights greater than 175, and then we found the z-score that went with that x. And then once we had that z-score, we used technology, in this case Desmos, to find the probability. And then we had our final answer. Now the reason I wanted to start with a problem from the last lesson was so that you could see how similar the new problems will be with the central limit theorem. This problem here is a central limit theorem problem. It starts off the same way, giving us some context about the mean and standard deviation. But now, instead of talking about one man and his weight, we're going to talk about 20 men and their average weight. This is what makes a problem a central limit theorem problem, is when instead of talking about an individual, you start talking about a group. Now, as we talked about with our rules earlier, the central limit theorem works if the n is greater than 30 or if the original population is normally distributed. In this problem, n is 20, which is not greater than 30, but we were told it came from a normally distributed population, so the central limit theorem can work here. Now here's the big difference between the two types of problems. When we're dealing with an individual value, we just use our typical normal distribution methods, which involve this z-score formula. When we're looking at a group and their sample mean rather than an individual value, now we're going to use a different z-score formula. That's the only difference in these problems, is it's a different z-score formula. If you notice, we still have the x, we still have the mu, and the only difference is the standard deviation formula. And that's because in a sampling distribution, the standard deviation doesn't equal sigma, it equals sigma from the original population divided by the square root of n. So the big thing you have to take away from this slide is if you're dealing with an individual data value, you use this formula. And if you're using a group of values, you're going to use this formula. And that's the central limit theorem. So in this particular problem, we're looking at 20 randomly selected men having a mean weight, average weight, greater than 175. That makes us a central limit theorem problem because we're not dealing with one individual, but we're dealing with a group. We're going to do things the same way. We're going to start by drawing a picture. The picture is going to be just like what we did before. 172 goes in the middle, 0 for the z-score. This time we're putting 175 over here, and we're going to need to find a z-score just like the last problem. But this time we're going to be using a different formula. The only thing that makes this problem different. So I take that 175 number, the number that was mentioned, my same mean from the beginning of the problem, the standard deviation from the beginning of the problem, and then our n is this 20 number, the sample size. And we get a z of 0.46. Now the rest of the problem is still going to be just like what we did in the previous lesson. I'm putting an x bar here because we're really talking about the average being greater than 175, not an individual data value. But I'm going to go to the same place on my calculator. We're going to use the normal dist, cumulative. Now I never drew the picture over here, but we wanted greater than 175, so we're going to go cumulative from that z-score of 0.46 to infinity. And that gives me a probability of 0.32, which is my final answer. Now if we take a second to go to the context of this problem, I want you to realize that we were calculating the probability that we exceeded the safety capacity of a boat. That means there's a 32% chance of that boat failing. That sounds way too risky for me, and I would want to design a boat that had a greater weight capacity. Let's do one more similar example. Let's assume Coke cans are filled to have a mean of 12 ounces and a standard deviation of 0.11 ounces. What's the probability that in a 36 can sample, we would have a sample mean of 12.19? Remember, this is a group, not an individual. So we're using our central limit theorem. Because of the size of this group being greater than 30, we don't need to know whether or not it's normally distributed. We know we can use this method. Anytime n's bigger than 30, we can use it. Let's take a second to draw our picture. Our z in the middle is always 0, and the mean is 12, so we're going to have 12 here. Now the x, or what's really an x bar, meaning a sample mean, is 12.19, and we're interested in that or greater. So I'm going to put 12.19 on the x-axis and shade to the right. We need to know a z-score for that x. Since we're using the central limit theorem, it's going to be the special formula that has the square root of n below sigma. So we have our x, or our x bar really, 12.19, minus our mean of 12, divided by our standard deviation of 0.11 over the square root of n, which in this case was 36. And my graphing calculator tells me that I get an answer of 10.36 as my z-score. So now that we know z, we can go and use our calculator to do the rest. The probability of x, or really x bar, being greater than 12.19 can be calculated by finding the area to the right of 10.36 in the normal distribution. And as you can see from Desmos, that's an extremely small probability. So small that we can't even see it on our graph. If you look on my graph right now, it cuts off at 4, which means 4 standard deviations, but we were asking for 10.36 standard deviations. So even if you tried to zoom in really far on 10, it's such a small probability, you wouldn't even be able to see the shading. With that 10 to the negative 25th, you'd have to write out that many zeros to start seeing this probability. When we get a probability that small, we can just say 0 plus, which means the probability is not actually 0, it's not impossible, but it's extremely low. And if we think back to the context of the problem, what it's saying is if Coke is really filling to have a mean of 12, and we collected 36 bottles that had a mean of 12.19, the chances of that happening are basically 0. So our real world takeaway would be Coke is probably not actually filling it to have an average of 12. It's very unlikely that we just got a very weird sample of 36 cans. It's much more likely that 12.19 is closer to the real mean than 12 is. And this is a way that statistics can be used to prove whether or not something's true. If you assume what Coke is telling you is true and get back this weird of a probability, it's a pretty safe bet that Coke isn't telling the truth. That's an idea we'll explore more in future units. To summarize this lesson, the only difference between this lesson and U4L2 is the z-score formula. Otherwise, the methods are the same. We use the U4L2 methods when we're considering the probability of an individual data value, and we use the L4 methods when we're considering a sample group and their sample mean. If you came away with anything else, write that down now. Otherwise, we'll see you in the next lesson.